First of all, let me thank the organizers for putting up this wonderful conference. So today, what I'm going to talk about is the title is Universal Bounds on Fluctuations in the Context of Thermal Machines. And I will try to connect our study with the so-called thermodynamic uncertainty relations. And I should right away thank Kay for already introducing very nicely about these relations. So I'll probably be brief in some of my slides. So I'm a faculty at IISER Pune. So if you are not aware where this institute is, so we are right in the western side of India, which is so this is a place called Pune, which is very close to Mumbai. It's about 150 kilometers from Bombay. Okay, so, and I should also right away thank my collaborators, also my PhD students, and my collaborator from Divya Segal's group at University of Toronto. So, so the key results that I'm going to present in today's talk are primarily based on these three references. So if you are interested in the technical details, please look at these papers. So with that, let me tell you the plan of the talk. So the first part, I'll be very brief and I'll try to introduce the key concepts about this so-called thermodynamic uncertainty relations in the context of quantum transport. And then I'll try to tell you some of the results that we obtained very recently regarding fluctuations in the context of thermal machines, bounds on fluctuations. Okay, so let me start with the introduction to thermodynamic uncertainty relations. So yeah, so what is TUR or thermodynamic uncertainty relation? So this was first came in the year 2015 by the seminal work by Barato and Seifert, where they proposed a trade-off bound, and the statement is basically the following. Imagine you have a system which is interacting with multiple terminals, and you have a system which is in a steady state because of multi-affinity. Given such a scenario, if you are in the linear response, meaning the affinities are not too large, then if you construct a quantity which is basically involving an entropy production rate and a relative uncertainty of a particular current, that means it's a ratio of the fluctuation of current over the average current square. So this is like the relative uncertainty, or if you want to say it's like a precision of your current, and that this product has a lower bound, and this bound is 1. Note that if you attended K's talk, there was a factor of 2, but that is here I have observed that in the expression of the fluctuation. So what basically it says that if you want to make your data precise, or if you want your output to be precise, you have to generate entropy. You have to pay a cost which is basically related to which is nothing but the entropy production rate. And how that is defined, if you have a multi-affinity system, is nothing but the product of affinity times current. And this is supposed to be universal in the linear response regime for arbitrary type of system, whether they're doing Markovian, non-Markovian dynamics, or any arbitrary dynamics. But for Markovian dynamics, as Kay pointed out, it's also valid beyond linear response. How do you prove? So I'll be focusing primarily in the linear response regime. And if you want to prove this, it's fairly simple. What you require is basically 2 central ingredients. One is Onsager's reciprocity relation. So we are focusing here time reversal systems, meaning the off-diagonal elements, your Onsager matrix is basically symmetric. And the other quantity is, other property that you need is the positive semi-definite property of the Onsager matrix. Now, given these two, you can show that this bound is always there. You can ask where is the equality happens. Well, you can reach equality if you have a single affinity, and if you are in the multi-affinity situation, you can reach equality if you are in the tight coupling regime, meaning the currents that you have within your system, they are proportional to each other, the average current. In that situation, you can reach the equality. So we have investigated this relation in various contexts over the past 3 or 4 years, and these are some of the references. If you're interested, please look into it. Now, what happens if you have this multi-affinity system and this TUR in the linear response? If you now try to massage this relation and try to construct the efficiency, you actually get a tighter bound compared to the Carnot bound in terms of fluctuations. Okay, so this is a universal bound. expressed now in terms of fluctuation, and the origin of this fluctuation, this particular bound, is just an outcome of the thermodynamic uncertainty relation. It also tells you something remarkable, which is that if you want to have a finite power output at Carnot efficiency, the only way you can get it by having a divergent power fluctuation. Okay, so that's a remarkable result that you get out of this thermodynamic uncertainty relation. On top of that, you not only get bound on efficiency, you also get bound on power. And given a typical engine where you have multi-affinities, you can talk about multi-currents. And for each current, you can write a TUR, right? So therefore, you can actually have the bounds on power in terms of all these various fluctuations corresponding to each current. So at this point, you can actually think of these as independent relations. Okay, these are independent bounds. But what I'm going to show you as we progress, that's not in the linear response. That's not really true. There is a strict hierarchy between these bounds. So that's going to be one of the central result in this talk. Okay, so as Kay also pointed out, that there are many works now involving thermodynamic uncertainty relations, and some of the experts are also in the audience. So I should not talk about this, where are the applications of these relations, but I'll quickly jump into the central results that we found very recently. So that brings me to the second part of this talk, which is the bounds on fluctuations. Okay. So what is the main result that I'm going to basically point out here? So the result is basically in this one single box. So you immediately understand what these expressions means. So eta average is the efficiency of a typical engine. I'll tell you more about it. Eta C square is nothing but the square of the Carnot efficiency. Now there is a new quantity, which is eta 2. I'll define that as we go along. But at this point, I'll just mention that this eta 2 is a ratio of fluctuation of your output over input. It's a ratio of fluctuations. Okay, so if you are looking at, for example, a thermoelectric engine, is the work fluctuation over absorbed heat fluctuation. So that's the quantity. Okay, so this is a result that is universal as long as you're in the linear response. So let me just quickly walk you through the proof of this relation. So we are going to focus on a very simple situation, having a two affinity situation. Okay, so imagine you have a thermoelectric kind of a setup where you can define two affinities, one involving chemical potential, another involving temperature difference. So given this kind of a situation, and we are going to focus in the linear response, so we can express currents in terms of Onsager's matrix and affinities. Okay, so here I changed my notation. I'm now expressing my current in terms of I not J, which I introduced before. So there will be some changes in the notation, but please pardon me for that. Okay, so this is a linear response. If you have time reversal system, which is the focus here, they are symmetric, the off-diagonal elements. Now, what I define is a relative uncertainty of individual currents, so which is nothing but the ratio of fluctuation over average squared. That's precisely the relative fluctuation that appears in the TUR. So what you can do is to construct the ratio of these two currents, relative fluctuation of these two currents. Okay, so this is 1 and 2 are basically two different currents that you have because of two affinities. And you try to express this relation, this quantity in the linear response regime. It's as simple as that. So if you do that, if you massage this relation, what you get is quantity 1 plus some certain thing. So this is like very similar like the way you go ahead and try to prove your TUR. But now look at this expression, which if you simplify, you actually see this expression is a product of two terms. And one is a very familiar object, which is like a determinant of the Onsager matrix. And then there is another term. Now, what happens is that because of the positivity of entropy production in the steady state, what you can simply show that this is nothing but is always have a definite sign, which is basically negative. Remember, it's L12 square minus L11 L22. So this is the negative of the determinant of Onsager matrix. So therefore, it's always negative, which is fine. So this has a definite sign. What about this guy? Now, that's where the crucial thing comes. If you allow your system, so at this point, I didn't impose any condition whatsoever that this setup works as a machine. Okay. Now, but if you want to define a machine, you really have to now identify your currents and set a proper direction for the currents, right? So you want to, for example, absorb heat from the hot terminal, and you want to deliver power. You want to take the work as an output. and heat as an input from the hot terminal. So once you set up these directions to make it a meaningful or useful engine, you can actually show that this is always also have a definite sign, which is less than 0. And that immediately implies, okay, so I'm going to prove that. I'm now going to show you that's what exactly happens. So if you now, for example, consider 1 as your input to your channel and 2 is the output, so then what it implies is that this guy has to be positive, which gives you a constraint on your Onsager coefficients and affinity. And similarly, if you want another current to be your output, that also gives you a constraint. If you merge these two constraints, you precisely get the condition that I showed in the previous slide. And as a result, what you get is the ratio of relative fluctuation. The ratio of the relative fluctuation of output over input is always greater than 1. What it also implies is basically the TUR, so now if you multiply your entropy production with this expression, what you simply obtain that the TUR product for the output current is always greater than TUR for input current. Now, this doesn't happen in general, but this happens when you realize your engine as realize your device as an engine. So you're putting extra condition, and these conditions are nothing but the directions of the currents in order to realize a machine. Okay, so that's the one of the central result of this. And as a consequence, if you now construct our eta 2, which is basically nothing but the ratio of the fluctuation of output over input, it gets bounded by the average of the efficiency square. And this is, just to reiterate, it's a universal, and as long as you're in the linear response regime. And it also, this particular result also immediately shows you that this fluctuation is going to be also less than eta c square. So there is a both lower and upper bound for the fluctuations. You can also read this result in a slightly different way. You can actually, what you have in this process, obtain a bound on the average efficiency in terms of the fluctuation. Okay, so if you take a square root, you're actually getting a bound on the average efficiency in terms of the fluctuation, which is also a tighter than the standard Carnot efficiency that we know from our macroscopic thermodynamics. And just to reiterate, this result is also independent of the bound that you receive from TUR. Okay, so because this is, in the TUR, you don't put these extra conditions of the direction of the currents. But now once you put that in, you actually get a completely independent and new bound. Okay, so so you can immediately verify and perform some numerics to test this result. So we did that for non-interacting coherent transport, as again, once again, K introduced in the context of electron transport. You can get the average current and fluctuations, just like what K presented, short noise, and all those factors will be there. And you can get into the linear response. And here what I show is that if you now construct this quantity, if you try to plot this as a function of gamma, which is the system path coupling, and the dot energy. So here I'm showing the plot for a single quantum dot coupled to 2 terminals and 2 affinities. So standard thermoelectric setup. You see these two plots are basically showing that both lower and upper bound are getting preserved. So that's basically setting forward what we have in our theory. Okay. And you can as well extend this. Is nothing specific about only a thermoelectric engine. You can as well extend this for other type of machines, for example, absorption refrigerator, which is also a very important type of thermal machine. And you can get a similar result where cooling efficiency now you have to talk about, which also gets similarly bounded, gets a lower and upper bound. So here, for example, what I show is a typical 4-level absorption refrigerator setup, which, so basically absorption refrigerator is doing what is absorbing current from the cold by taking help of the ultra hot work terminal and channelizing current to the hot, right? And it has a particular sequence of this temperature that it needs to follow. And once again, here the higher the result that I showed, that the TUR for output is larger than input, the precisely, once again, you have to feed in the information that the directions of currents are fixed, because that's how you realize a refrigerator, right? So here, once again, what I show is that both the upper and lower bounds are getting respected. If, for example, if you make G tends to 0, which is the splitting between level 2 and 3, if G is very small, you basically reach to a tight coupling regime. And in this regime, all these bounds basically, this lower bound saturates, which is nothing but this empty circles and triangular And if you make G large, which is basically the first two, you actually don't satisfy the tight coupling, and therefore you have a difference, but the bound certainly gets respected. Okay, so now connecting to what I just said for two affinity problem, if you once again extend this, as I in the last slide, as I mentioned, for the absorption refrigerator, just to recall what TUR gave us. The TUR, sorry, here is a typo, it should be 1. So TUR gave us, TUR is basically this, which gives us bounds, 3 independent bounds, as I was telling you, from the TUR, which is basically expressed in terms of corresponding fluctuations of either cold, hot, or work terminal, which I'm denoting as this PC, pH, and PW, this entire expression. And you also receive a bound in the efficiency, which I'm denoting here IEC. Now, just like before, similar calculation if you perform by setting the directions of the currents to realize absorption refrigerator. That means you put this condition that your currents are JC and JW are positive, meaning that so my convention of positive current, meaning the current is flowing towards the system. So you want both cold and work current to flow within the system, and you want to deliver, or everything want to dump into the hot terminal. Once you put this condition, you see a strong hierarchy that comes out just from what I presented in the previous case. So a cold, hot, and W, this particular hierarchy comes out. And because of that, your output power, which was initially supposed to be independent, that the TUR predicts that these 3 bounds for power is independent, is not really true. Once you set this condition, there is a strong hierarchy, and the bound gets strongly determined or tightly determined by the fluctuation of the by the fluctuation of the work terminal. So there is a hierarchy in the linear response. And as I mentioned, because of this hierarchy, we get a completely different bound than what is predicted from TUR, and that is given here. And turns out that this bound can be tighter than what is predicted from TUR. So therefore, it's also important to consider. And similarly, you do get also another bound on the output power. And all these bounds, one can argue that if you take the tight coupling limit, meaning the currents within the system are proportional to each other, they actually saturate. So here I once again show the results for the full level system, which is so this setup takes you beyond the tight coupling if your G is finite or comparable to these gaps. But if G is small, then you actually reach to the tight coupling limit. So here we basically model all these transitions by the rates, and the rates are governed by the standard thermal factor times the hybridization element. So these are details that I don't want to talk about, but here is one central result that I want to show. So if you are beyond tight coupling, you don't saturate the bound, and what you get is basically, let's focus on this. You have the output power, which is this blue line. And if you see now PW, PH, and PC, as I mentioned, the bound gets tightly bounded. The power gets tightly bounded by the work, and that's what you see here. Okay, so there is a strong hierarchy between cold, hot, and W. However, this particular bound that I mentioned, which is predicted completely independent of TUR, that can sit anywhere. So that doesn't follow this hierarchy. So this particular bound can be anywhere between this. Okay, but if you just compare the bounds that follow from TUR, they obey a strict hierarchy. And similarly, if you look at for the efficiency, TUR predicts the yellow line. Now, because of this extra constraint that we put in, the new bound that we receive, which is square root of DC by dW, that can be tighter. And this is the original efficiency that you have. So this is completely independent of what you receive from TUR. If you go to the tight coupling by making G to become much, much smaller than the gaps, as I mentioned, they all saturate and predict squareless with the actual value of the efficiency and the power. You can extend this study for other models. I mean, here the main motivation was that it's not limited to any weak system bath coupling. You can actually do it for strong system bath coupling and so on. So there is a 2-level weakly coupled to 3 baths doesn't have a absorption refrigerator working condition. But if you couple it strongly, you do get that. And similarly here, as you can show that this hierarchy gets obeyed, and this particular bound can sit anywhere within this hierarchy. And similarly, same thing happens as well for the efficiency. So this is just to show a scatter plot, just to point out that this bound that we receive by putting these extra conditions can become tighter than what is predicted from the TUR. And as you see from these two plots for both 4-level and 2-level, there is significant parameter regime where you can find this bound to be tighter than this. So therefore, it becomes important to consider. So with that, let me just conclude. So one of the main message that I wanted to give out is that if you are in the useful operational regime, whether whether it's a heat engine or a refrigerator, these TUR relations are the bounds that you receive from TUR relations are not independent, but there is a strict hierarchy between these different currents. And as a result, you get new bounds on both efficiency and output power for thermal machines, given in terms of fluctuations. So with that, I want to thank you for your attention.
Thank you very much, Bijay. That was a great talk.
Thank you, Kay.
Very quick question for clarification. When you talk about average efficiency, that's the normal efficiency. It's the ratio of average currents, right?
Absolutely, yes.
Yeah, okay. So this efficiency is not fluctuating.
No, so it's average. It's not the stochastic efficiency. It's the efficiency of ratio of two average currents. That's it.
Okay.